Hi everybody, so this is just a review on the Respiratory Physiology laboratory. I'm going to go back up here and show you the heading there. So this is the first, or I should say the main packet, along with all your Respiratory Physiology lab packets. And what I'm going to do is I'm just going to go through a quick little tutorial going through these exercises for you, trying to simulate this experience as best as I can. So the first activity here is very simple. We just ask people to breathe on a watch glass. A watch glass is, actually, you know what I'm going to do is I'm just going to show you what a watch glass is. Just go to our friend Google here. Watch glass. All right, so this is what a watch glass is. It's kind of hard to describe, actually. So this is what we have at all the benches in the lab. Oh, and here, the information on how to purchase one yourself. Please don't go and purchase one yourself. But anyways, we have these out at the benches for you, and we just ask people to breathe on them. And of course, when you breathe on it, just like any type of glass surface, you're going to see condensation. So what is condensation? Condensation is where the gaseous form of water within the air that you breathe comes out, and this is not necessarily in the context of the air that you breathe, but this is the context we're talking about here. So in this case, the air that you're exhaling, more specifically, has a lot of water vapor in it. Water vapor is the gaseous form of water. It has a lot of water vapor in it because it's warmer than the ambient air within the room. So the air within the room is at room temperature, which is about 20 degrees C. The air within your respiratory tract that you just exhaled is a lot warmer. Now, it doesn't go all the way up to your basal body temperature, which is 37 degrees C, but it gets up there pretty close. And if you go all the way down to the level of the alveoli, the temperature will be at 37 degrees C, your basal body temperature. So the air is much warmer than the ambient temperature, and because of that, it can hold a lot more water in its gaseous form, aka water vapor. Now, immediately when you exhale the air, then there's a temperature drop for the air, and as a result, it can't hold as much water, and so the water comes out of the gaseous form, or I should say a better way to say it, a more elegant way to say it would be that the air, or rather the water vapor, the water in its gaseous form transitions to the liquid form, and that is apparent in the form of condensation on this glass surface. So I'm going to write it out for you. So got to initiate my little pen tool here. So condensation forms on the plate. That's your observation. And now here's the explanation. Air exhaled is warmer than the ambient air, that is the air within the room. The exhaled air cools when leaving the respiratory tract. As a result, it can hold less water vapor, and the resulting liquid water condenses on the solid surface, that is the surface of the watch glass, or the watch plate, that is. Okay, so the next activity here requires you to get out a thermometer and basically exhale, breathe out on the bulb of the thermometer. That is where the, well, it's not mercury anymore, but whatever substance they put in there that is sensitive to temperature changes. So basically what's going to happen is you're going to see the reading on the temperature go up. So the temperature of the thermometer, or the thermometer guess the best way to say it is the temperature of which the thermometer reads should be your ambient air temperature until, that is, you breathe on it, in which case the temperature should go up, right? Makes sense. Nothing earth-shattering there with that result. So in other words, the thermometer should read approximately 20 degrees C, which is the temperature of ambient air, that is the air in the room, breathing on the bulb of the thermometer will increase the temperature read on the thermometer because exhaled air has a higher temperature than the ambient air. All right. Now things get just a little bit more complex. Not too much complex, but a little bit more complex. So now we're going to mix together some solutions. So we're going to start off with lime water, an aqueous solution of lime water. So that is this calcium hydroxide dissolved within water. And what we're going to ask people to do is we're going to ask them to take out a straw and exhale into the straw, which is also making contact with the solution of calcium hydroxide. By the way, calcium hydroxide is lime water. It's called lime water. So as you add CO2, which is contained within the air that you exhale, to the calcium hydroxide, it reacts to form a solid precipitate, which is the calcium carbonate. This is calcium carbonate. And then water. So there's water everywhere in the solution, so this water goes and joins its friends. But what really stands out is the fact that we now have this solid precipitate, calcium carbonate, in the solution. So I'm just going to come out and tell you that the calcium carbonate solution, or I'm sorry, not the calcium carbonate solution, the calcium hydroxide solution, the lime water solution that we begin with, is clear. When you exhale into the solution through the straw and form the calcium carbonate precipitate, then the solution turns kind of a milky white color. And that's because the calcium carbonate precipitate is white. All right, so to fill in this properly, we would say when CO2 mixes with calcium hydroxide, you form calcium carbonate and water. The calcium carbonate is a white precipitate. Precipitates are solid, by the way. So, in other words, the calcium carbonate comes out of solution. As a result, the clear lime water will turn white, this chemical reaction simply demonstrates that we, messed up there, exhale CO2. All right, that's it. So this simple chemical reaction here is meant as a setup for the next chemical reaction, which is a little bit more complex. So now you get the concept that we're basically forming an assay, if you will, a means of measuring something based on a simple chemical reaction through which we're measuring the levels of CO2 based on how fast it takes to change this solution. So in other words, the more CO2 you have every time you exhale, or the more times you exhale, the faster you're going to see the formation of this precipitate, and so the faster the solution is going to change. So now we're going to set up another series of chemical reactions which are going to change the color of the solution according to the amount of CO2 that is injected or added into the solution. However, the reactants are a little bit different and the color change is different. All right, so we're applying the same concept to a new series of chemical reactions, but the aim is the same. We want to be able to extrapolate how much CO2 we're actually putting into the system based on the changing of the color. All right, so let me switch back to our marker here. So phenolphthalein is an acid-base indicator dye, which is purple in an alkaline or basic solution. Remember, alkaline means the solution is basic, which means the pH is greater than 7. So, however, in a neutral solution, that is a pH of about 7, the purple color fades and becomes colorless. So phenolphthalein is colorless at neutral pH, and it's also going to be colorless at acidic pHs as well. So what does phenolphthalein allow us to detect? It allows us to detect basic pHs. But on the flip side, we could also say that if the phenolphthalein is not purple, or it's not evident as having this bright purple color, then we could say that it also allows us to detect neutral pHs. Does that make sense? Or acidic pHs. But we're not making solutions with acidic pH. We're just going to make a solution with a neutral pH. So this is what people really struggle with. We're using the phenolphthalein indicator dye so that we're able to determine whether the solution is neutral. Even though the phenolphthalein indicator dye produces this nice, pretty purple color, during basic solutions, we don't really care so much about the purple color. We care about the change from purple to clear in the case of this simple assay that we're setting up. So I want you to keep that in mind as we go through this. What we're really going to be looking for is a color change from purple to clear, not the other way around. That's very important. Okay. So what we're going to do is we're going to use the phenolphthalein indicator dye to figure out when enough carbonic acid, this is carbonic acid right here, let me underline it, carbonic acid, H2CO3, is formed in order to neutralize the sodium hydroxide in a sodium hydroxide solution. So what does that mean? Don't worry if you're confused. I'm going to go through it step by step. So this is what we're starting off with. We're starting off with an aqueous solution, that means a water-based solution of sodium hydroxide. And that's what these directions indicate to you right here. So I'm going to draw out these directions for you down here at the bottom. So let's switch colors. So it's a little bit more. Let's do black for our glassware. So we're going to start off with a big beaker that holds 200 milliliters. And we're going to fill it up with an aqueous solution of sodium hydroxide. So what we're going to do in order to make that aqueous solution is first we're going to fill up the bottle, or rather the beaker, the beaker. With 200 milliliters of water, approximately. And then we're going to add 10 milliliters of sodium hydroxide solution. And as a result of this, we now have a basic solution, or an alkaline solution, because sodium hydroxide is a powerful base. So now we have 200 milliliters of a nice basic solution of sodium hydroxide. The next thing we're going to add is we're going to add a couple drops of the phenolphthalein. And as soon as we add the phenolphthalein is going to do what it does best, and that is change colors. Remember, in basic solutions, the phenolphthalein is a nice, brilliant purple color. So that's what our aqueous sodium hydroxide solution is going to look like now. All right. So the next thing we're going to do is we're going to then split up the solution into two smaller beakers, which hold approximately 100 milliliters, right? Because remember, we have 200 milliliters here, so now we're going to split up this solution in even 100 milliliter amounts as best as we can. So here are our two smaller beakers, both containing 100 milliliters of this aqueous solution. So let me get the blue. So you can see the air fluid level here. And then we'll get out our purple to remind ourselves that this basic solution is purple because it has the phenolphthalein pH indicator dye in it. All right. So the next thing we're going to do is we are going to ask someone to, sorry, I'm going to change colors here. There we go. We're going to ask someone to insert a straw into one of these beakers with the sodium hydroxide solution in it. And they are going to exhale into the straw, and we're going to time the amount of time it takes for the solution to turn clear. So why would the solution turn clear? That's where we come back up to this equation. What happens is the CO2 that we exhale with each breath reacts with water in this aqueous solution of sodium hydroxide to form carbonic acid. Remember, carbonic acid is H2CO3. Now, carbonic acid immediately falls apart, which you should be learning about in lecture, into a proton or a hydrogen ion, same thing, and bicarbonate. So bicarbonate is a polyatomic ion. That means it's a molecule with a charge on it. It happens to have a negative charge on it. Now, in our blood plasma, the most common cation is sodium. So in our blood plasma, this isn't blood plasma, but if it was our blood plasma, you'd have this bicarbonate anion associating with the sodium cation very regularly. They like to hang out together, right, because opposites attract. Sodium bicarbonate, by the way, is baking soda. That's what baking soda is. And it turns out that bicarbonate is a very, very effective buffer. So buffers are any type of chemicals which are very good when put in an aqueous solution of absorbing excess protons or hydrogen ions or excess hydroxide ions. And you should know from your basic understanding of acids and bases, if you have too many hydrogen ions or protons, then you have an acidic solution. And if you have too many hydroxide ions, by the way, hydroxide ions are OH minus. If you have too many of these things, then you have a base. Now, why would we have a base in the sodium hydroxide solution? Well, when you dissolve the sodium hydroxide, into the aqueous solution, the water-based solution, you get sodium ions and, what do you know, hydroxide ions. So that's what makes this such a strong base. So what happens is the bicarbonate is going to absorb excess hydroxide ions like a sponge, right? So it's like a base sponge. And as a result, the pH of the solution is going to go down. It's going to become more neutral. All right, so as a result of that neutral pH, what's going to happen to the phenolphthalein indicator dye? The phenolphthalein indicator dye is going to go from purple to clear. So as a result, the more CO2 we inject into the solution, the more carbonic acid we form, the more bicarbonate we form, and the more that bicarbonate then sucks up all of that excess hydroxide like a sponge. And as a result, the solution's pH is going to go down. Does that make sense to everybody? You don't have to worry. And by the way, what's really going on here is that on a chemical basis is, and this is getting a really, really technical, and you won't have to know this for the sake of the practical, but the teacher in me just can't let it go. When you form this particular molecule from carbonic acid falling apart, or this particular polyatomic ion, bicarbonate, in reality, what you end up doing is you end up forming a lot of extra protons, and it's really the protons that react with the hydroxide to form water. But in any event, I wanted to point out to you that the bicarbonate ion is a powerful base, or rather, I'm sorry, is a powerful buffer. In general, buffers absorb excess protons and excess hydroxide ions. It just turns out that the way this buffer works is that by forming excess protons, those protons will then react with the excess hydroxide ions in order to give water. Likewise, if you had excess protons, meaning you had an acidic solution, then what would happen would be that the protons, or the hydrogen ions, would react directly with the bicarbonate, and the bicarbonate would act like a sponge and suck up all of those excess protons or hydrogen ions. In any event, this is what you need to know, is bicarbonate is a powerful buffer. Buffers neutralize solutions. This solution started off as a basic solution. When we add bicarbonate, we now have a neutral solution. How do we know we have a neutral solution? Because we have the phenolphthalein indicator dye. So the solution is going to go from being purple to being clear. And so what's going to happen right here is our solution. Oh, come on. I want to write. There we go. So our solution is going to go from purple to clear as we exhale into it. That's all we want you to know here. So what we're doing is we're measuring the time that it takes. We draw in like a little, actually no, that's not what I meant to draw. That's what it looks like. There we go. That's what I meant to draw. There we go. So this is like a little stopwatch, I guess. So we measure the amount of time that it takes for the solution to go from purple to clear. Now, we do the same thing, except that that same person that just exhaled into the other solution is going to exhale into this beaker with the same solution, with the sodium hydroxide and phenolphthalein dissolved within it, is going to exhale after 2 minutes of vigorous exercise. So 2 minutes of exercise. So usually we ask someone to go and run to spring hall or do jumping jacks or push-ups or something. But anyways, whatever you do, it has to be for straight 2 minutes. And so after that person is exhausted and you're breathing heavily, they then go and exhale into the other beaker, and we time the amount of time that it takes for the solution to, again, go from purple to clear. For some reason, the width on my pencil changed on its own, and I don't know why that is, but I'm going to change it back to 1. Okay, there we go. So then we asked you to compare the two times. So which setup do you think is going to take less time? The setup where you're just breathing into the solution at rest, or the setup where you're breathing into the solution after 2 minutes of vigorous exercise? So what we always find is that the solution takes a lot less time to turn clear when the person has just performed 2 minutes of vigorous exercise. And why is that? Well, remember, what are we really measuring by this simple little assay? By measuring the time that it takes for the solution to turn clear, that time is a proxy for the amount of CO2 that the person is exhaling, right? So the more CO2 they're exhaling, the more carbonic acid forms, the more bicarbonate forms, and the more quickly the solution neutralizes and the more quickly the solution turns clear. So why would the person exercising be exhaling more CO2? That's the next question. So let me just write this all out so you guys can follow along with the story. It takes less time for the sodium hydroxide, phenyl, phthalate solution to turn clear when exhaling into the solution after exercise, because the increased physical activity increases your cellular metabolism, that is, i.e., within the skeletal muscles. Which results in increased CO2 generation, right? Because when the increased metabolic activity in the skeletal muscles results in the increased consumption of oxygen, in return you're also going to get more CO2, right? So this leads to elevated levels of CO2 in the blood, and this is via internal respiration, right? Internal respiration is where we have gas exchange at the level of the blood vessels and the tissues, that is, more specifically, the blood vessels over systemic circulation and those tissues which those blood vessels service via internal respiration. So CO2 is leaving the cells and going into the capillaries that service those cells. Likewise, more CO2 will leave the blood during external respiration as well. So remember, external respiration is the gas exchange that's occurring between the gas in the alveoli and the capillaries surrounding those alveoli. So more CO2 is going to leave the capillaries surrounding the alveoli and enter the gas-filled alveoli. So as a result, each time we exhale, we are exhaling greater amounts of CO2 from our alveoli. That is with exercise, right? And the elevated levels of CO2 in the exhaled air lead to the faster formation of carbonic acid in the sodium hydroxide phenolphthalein solution. As a result, the pH of the solution neutralizes faster and the solution turns clear faster. All right, and that's all there is to that. So the next activity, page 4, will be a separate video tutorial. I hope this helps. See you soon.